Hello, we're going to talk about the correlation hypothesis testing situation. Our scenario is, do people walk faster as the weather gets colder on UW campus? Throughout last semester, on 15 different days, Jared's walking speed in miles per hour and the daily high temperature in Fahrenheit were measured. And then it gives the results of the covariance and two variances. So we first need to determine the hypothesis testing situation. So I'm going to start with the two variables in this case. And so our two variables are the walking speed and the daily temperature. Those are the two variables that we measured. And the level of measurement for both is ratio. Now, this one's a little tricky. There is only one sample in this case. And initially, you might think it's Jared is the one sample, but what is actually being measured is the walking speed and daily temperature is not on Jared per se, but on the 15 different days. So the 15 days is what gets us to a different walking speed and a different daily high temperature. So we have one sample, two variables. Both of those variables have ratio level of measurement. This is why the test situation is correlation. The other thing we need to figure out is the question of interest, which is right here. That is our question of interest. And so now that we know that the test situation is correlation and that we have the question of interest, we can determine the hypotheses. So the null hypothesis uses R, and R represents the correlation, or the more particularly the population correlation. And what we initially assume is that the correlation is 0. Or in other words, there is no correlation between the two variables. Now, the alternative hypothesis is an R and it's a 0. And we need to determine, is it a greater than, is it a less than, or is it a not equal to? And what we need to consider here is this question of interest. Do people walk faster as the weather gets colder? And so what I like to do is, if you think about how a scatter plot works with your two variables, and it doesn't matter where you put what, which variable on which axis. So I can do temp here and speed here. So we're saying people walk faster as the weather gets colder. So cold weather is here, lower temperature is going with higher speed. And so if you kind of think about a dot there, well, then if you look at this in the reverse, walking slower with higher temperatures gets you a dot there. And that's kind of then the extremes of how this is going on. And then if you draw a line between them, you end up with this negative slope. And so what the question is about a negative correlation, which is why we have a less than in the alternative hypothesis. And so what this is really saying, generally low temperatures, high speeds over here, high temperatures, low speeds. That would be a negative correlation. And then if the question of interest happened to go the other way, you'd have something like that. That would be a positive slope, and that would get you to a positive correlation. And so we can write these hypotheses in English. And so what's going on here is we're talking about correlation or being related. And so Jared's walking speed is one of the variables, and the outside temperature is the other variable. And we're saying they're not related to each other. And so if two things are not related to each other, that is a correlation of 0. That's the null hypothesis. Now, our alternative in symbols was r is less than 0. And so I can write this in a couple of different ways. The first variable, Jared's walking speed, the second variable, outside temperature, is negatively related or negatively correlated. And so that negative is the why it's a less than in this case. Now, this is a little bit kind of statistical jargon here with this negatively related. And that's why we can actually write this in a different way and just say, Jared walks faster when it's colder outside. That has the same meaning as saying Jared's walking speed is negatively related to the outside temperature. So this first way of doing the alternative hypothesis in English is more of a direct translation to the alternative hypothesis in symbols. And this second way of doing it is more of practically what's going on and maybe more easy to understand. Now, you only need one way to write the alternative hypothesis, but these are just two examples of things that are equivalent to one another. Now that we know the test situation, the hypotheses, we need the critical value or values. And so delta in this case is equal to the sample size, 15, the 15 days, minus 2, which equals 13. The null distribution for the correlation hypothesis testing situation is the t distribution. And so now we know, because it's the t distribution, we're going to look up the t table. We're going to come down here to the t table. The degrees of freedom is 13. So we know we're going to be in this row. And now we look at the alternative hypothesis, r less than 0. So this alternative hypothesis is important. This alternative leads me to using the 0.05 column. And so I know we are going to have a critical value, and we've got the 1.771, but because of this less than here, we use the negative of that. So I use the 0.05 column because it's a less than alternative hypothesis, and the negative in the making the critical value negative because of the less than in the alternative hypothesis. Now we can determine the test statistic. So I'm going to write the equation of the test statistic right here. And the equation of the test statistic is the sample correlation all over the square root of 1 minus the sample correlation squared divided by n minus 2. Now, we were not given the sample correlation. We were given the covariance and the variance of each of the variables. And so the sample correlation is the covariance divided by the standard deviations of each of the variables. So x and y are just the generic two variables. which is really the same thing as the covariance of the square root of the variances. So my sample correlation is equal to the negative 26.6. That's the covariance. And then it's the square root of the 361 times 4. All of that is under the square root. And that's how you calculate a correlation from the covariance and variances. So when we do this calculation, you get a negative 0.7. And so really, as you should have read in chapter 17 of the book on correlation hypothesis testing, a correlation is between -1 and 1, and a correlation closer to 1 or -1 means a higher relationship between the variables. Well, all a correlation really is a rescaling of this covariance to being between -1 and 1. And so whatever sign the covariance is, it's negative in this case. That's why the correlation is negative, because the variances and alternatively the square root of the variances, which is the standard deviations, are always going to be positives. So now that we know sample correlation, we can get the test statistic, negative 0.7 divided by the square root, and this is 1 minus, and then it's negative 0.7 squared all over n minus 2, excuse me, minus 2. Now, I put parentheses around that negative 0.7 because when you square that, you're going to get a positive value. So you're always going to get 1 minus some positive value. Some people have a hard time doing this in their calculator, and their calculator gives an error of you are trying to take the square root of a negative value. Well, you're never going to get a negative value here because you're always going to do 1 minus something, some positive number that is going to be less than 1, because the correlation is between -1 and 1. You square that, you're always going to get a number between 0 and 1. So when we do that calculation, we get a negative 3.534. That's the value of the test statistic. And so now that we have the value of the test statistic, we can get the probability statement for the p-value. And so that's going to be the probability. We're going to use t because that's the null distribution. It's going to be a less than because there was a less than in the alternative hypothesis. And then it's the value of the test statistic, which is the same thing as saying 1 multiplied by this probability statement. And we don't use absolute values in this case because of the alternative hypothesis. So the alternative hypothesis dictates what the critical values are, how the probability statement is for the p-value, and that's true in all hypothesis testing situations, including here with correlation. And so as a reminder, we found that critical value up here. Write that down one more time. And so we can compare the critical value to the test statistic to make our statistical decision. And so we are going to reject the null because negative 3.534, the test statistic is less than negative 1.771, the critical value. So now that we have our statistical decision, we can get to the conclusion or interpretation. So I conclude, and then right there between those is just the alternative hypothesis in English. And then our specifically part is really explaining what it means to have a negative correlation. So, specifically, Jared walks faster when it is colder outside. The reason why we don't include the value of the negative zero point 0.7 is because we can really only interpret the sign or the direction of the correlation. Because if I have this correlation, or I have this correlation, or I have this correlation, they all have the same meaning. Jared walks faster when it is colder outside. The magnitude of the correlation is really talking about the strength of the relationship. And that's really talking about when you think about things, are the dots kind of really spread out? And we're really thinking this kind of a direction, are they really spread out? Versus in this direction, there's very little spread. And this is going to have a higher correlation for this plot than it is for this plot. I did draw these in a positive direction, but the same thing applies in the negative direction. And so this one is going to have larger in magnitude, meaning a larger negative number, closer to -1 than this guy up here. And again, there's examples in the book in chapter 17 about scatter plots with different correlation values.